fact is not totally true, because, well, cockroaches, we think of them as reviled. They are reviled as a scourge of urban living, but in reality, they don't only live in dumps. There are like 4,000 species of cockroaches living in the wild. And now we see something that resembles to New York, but in fact is just like buildings made of garbage. And one of the main, so this company, BNL, is one of the main who caused this problem. And I hope that doesn't sound very familiar. So this story have like 4 main characters. We have seen like the cockroach and the plant are like the living things, but also they sent this white robot here on the top left corner to look for, she's searching for life in form of plants. So humans who essentially were evacuated because of the harsh conditions on Earth, they now live out in space in a spaceship. So we see that they are now fat because they don't exercise. They essentially live looking at screens, and robots actually look after them. I hope also that doesn't sound very familiar. But something that is actually a part of, it's not really science fiction anymore, is this premise that the Earth actually is in a crisis. So we have scientific evidence that glaciers are melting. Some of them have already disappeared. Sea levels are rising, cloud forests are drying, and wildlife is struggling in general. This is because of the greenhouse gases due to human activity that is causing a set of changes to the Earth's climate. But moving on to the astronomy part of the movie, here when Wally goes after Eve, the white robot that I showed you, so he fell in love with Eve, and now they are taking back Eve to the spaceship where humans live. So now this scene is very familiar because this happens on Earth like very often, spaceships just leaving the Earth. And now it's not very clear to me. So Wally is here hooking from the outside of the spaceship, and now they are crossing the atmosphere. You can see now, and this is pretty shocking, that humans not only polluted the Earth like here, but also the space, the immediate surroundings, the immediate orbits of Earth. And now we see that it's all, we call this space debris. So it's very nice that we see here Sputnik, which was the first artificial satellite sent by the Russians in the 50s. This scene is actually pretty shocking because this is the first time Wally sees the stars, inside the Earth with so much pollution. This is not possible. This is a problem that actually already happens in many of the major cities. And now he looks back and he sees this brown Earth. So currently the Earth would look blue because of the large amount of water bodies that we have. So this is pretty sad. So he wasn't able to see the sky. Now we see that he is experimenting something that we call zero gravity. So gravity essentially decreases with distance. And now, now they are traveling through the solar system. We see here the moon, and all of the sudden they are going to show up near the sun. This is kind of realistic because in space traveling, we don't have unlimited fuel, which is actually something.
I think just checking yourself for questions like axis, they might not necessarily know what that means. Like just maybe just have a quick look through and like just think, okay, would a someone who's maybe done science at primary level but not seen a graph.
Okay. So here we're seeing I was saying that in space we kind of travel visiting orbits. So for instance, we visited the moon orbit to take impulse to reach outer orbits. So that's actually a very good point. Here we are seeing a solar flare. So a solar flare, in fact, is part of the activity of the sun. The spaceship here is like dangerously close to the sun. This is not something that happens in reality. There is, NASA has sent one, the Parker probe, that is the one that studies solar activity and has reached the closest to the sun. But overall, like the temperature is really, really high. So it's like thousands of Kelvin. And the corona of the sun is in fact millions of degrees. Here, Wally is recharging with solar energy. And now all of a sudden they are visiting Saturn. This is Saturn's rings, which they are thought to be made of like collapsed moons and comets. They were torn apart by the strong gravity of Saturn, because Saturn is the second largest planet in the solar system. It's about 10 times the size of the Earth. Here he is looking at some galaxy. We are going to assume in this movie that they are traveling in the Milky Way. So it's not like they are visiting other galaxies. So that galaxy that we are seeing there might be probably something like Andromeda. And for instance, here we see another star. This very white path that we see in the background is something that we can actually see from Earth if we, in a very dark night, if we look at the sky. And now the spaceship is arriving to a nebula where the main spaceship is kind of parked. And this nebula, in fact, is very interesting because here I am showing the pillars of creation, which is an image taken by the Hubble Space Telescope, which is a real nebula. Here we see visible on the left, and then infrared, I think, is on the right. And this is important because all these images, in fact, are processed. So, for instance, in the movie, while you see all these beautiful things with colors, etc., with his robot eyes, but we humans, in fact, need some processing. And so, essentially, nebulae, they are nurseries of stars. So maybe they are using it as a reference that humanity is being reborn in one of these nebulae. Okay, going back to the debris problem. So very briefly, I'm going to mention that this is actually happening today. We have the situation of Starlink, which is a satellite network operated by SpaceX to provide with internet access, which is very nice. So this is to most of the Earth, even remote places. But this translates into 1,600 satellites, which in turn, this is going to be eventually spatial debris. They estimate to have a mega constellation of approximately 40,000 satellites. And of course, this is a problem for astronomers because not only is going to interfere with observations, but it's going to, very sadly, is going to damage our dark sky at night. So we won't be able to see any of what we see. So some numbers from the European Space Agency, like about 12,000 satellites have been launched to Earth's orbit, and more than 500 collisions and breakups have happened up there. And this translates into about 1 million of particles that are larger than 1 centimeter, but even, I don't know, like 300 millions of particles that are smaller than 1 centimeter. So these are some estimates from simulations, and it's pretty shocking. So yeah, that's actually a realistic problem from the Earth. Sorry, that the movie addresses about the Earth. This scene here is actually also very interesting because it addresses the problem of moving through space. It's not very intuitive for us how this works. Of course, you need some kind of propulsion to move through space, but something that they don't really address very well is that how time works in space. So motion through space actually creates alterations in the flow of time, as we know from Einstein. So that's very, very, very good. Well, by the end of this scene, Wally manages to take the plant out of his little box. And that is, of course, not true, because plants cannot survive in such harsh environments. Yeah, like this here. And that's it from me. So essentially, humanity manages to come back to Earth. And here we see them like all happy. The plants survived. Temperature, well, plants in fact require like water and the right temperature and sunlight. So in space it's actually very cold. And whenever, for instance, astronauts come back to Earth, they actually struggle a lot with the strong gravity that we have here. Thank you very much, and I'm happy to take some questions.
Hi, thanks, Teresita. I think I'm handing over to Mike now to ask any questions that are coming through from any of you attending. So feel free to type any questions into the question and answer box. Teresita, can I ask you to stop sharing your screen?
Yeah. Okay.
Thank you.
Thank you.
There aren't any questions there. So I suppose, like, Mike, do you have anything you want to ask? Otherwise, I'll ask a question.
Well, I was really shocked by the number of objects that sort of float in the sky, sort of obscuring our view of the night sky. So you give some estimates, but do you think people are trying to help with the situation? Are there plans to stop more space junk accumulating in space?
I think, in fact, this is something nice about astronomy, because I have read some projects that are addressing the problem, but the main problem is that we cannot really sweep all the debris and then bring it back to Earth, because that requires a lot of energy. The space actually is huge. So it's really, these are like particles that are smaller than 1 centimeter. So it's actually pretty much impossible. And in any case, it's gonna get worse, because companies such as SpaceX, they are thinking on sending even more and more satellites, which is sad. But on the other hand, we also benefit a lot from all this technology, as we are experiencing right now.
Yeah, it's a very fine balance. Any other questions from the audience? There's just the Q&A button at the bottom if you want to pop a question in.
Yeah, and if any questions come up later, you can type them in the Q&A, and Teresita will keep an eye on the Q&A there as well and be able to type any responses. So if something comes to you later on, that's also fine. But as it doesn't seem like anything's coming up just now, I'm going to pass on to our next speaker today. So our next speaker is Andy. So Andy, I'm going to spotlight you and hand over.
All right, hello everybody. Hopefully you can hear me now. Oh, there we go. Yeah, so I've got the lovely background of the Royal Observatory behind me, but I'm going to start by turning that off, because it will make things a bit simpler later. So now you can see the real world behind me. It's like the Matrix, where suddenly you see what reality is actually like. Okay, I'm going to start by showing you a picture. So here is some stars. And you see there's some bright stars in that picture, just a few, and you might recognize them because they're stars you can see with your naked eye. It's the Plough, or Ursa Major, or the Big Dipper. It goes by many different names. So you can see those with your own eyes, and hopefully some of you recognize those stars. In the background, there are lots and lots of very faint stars. Now, those you can't see with your naked eye. We've taken this picture with a big telescope and a long exposure. And you might think, well, okay, that probably means that those bright stars in the Plough, they're probably very near, and the other ones are much further away. And that's probably roughly true, but then you think, no, hang on, how do we know that's right? Because it could be that the Plough stars are like super powerful, and the other ones are just terribly dim. Just like there are some people that are really tall and some people that are very short. So how do we know what's correct? In fact, in general, how do we know how far away those stars are? Because, you know, we can't go and visit them. So we can't exactly kind of step it out with a measuring stick and know how far away those stars are. So how do we do it? Well, the person who first did this was, in fact, the very first Astronomer Royal for Scotland. You can see there, Thomas Henderson. And the other person in the picture, that young man with his finger up, is showing us how he did it, an effect called parallax. Now, I'm going to get you all to do an experiment. So I'm going to stop showing my screen and show you what I mean. This is what I want you all to do at home, if you could. First of all, look at something at the far side of your room and keep your eye fixed on it, okay? Hopefully the further away, the better. Then stick your finger up in front of your nose like this, and then shut one eye and then the other eye, like that. And you see, what you'll see is your finger, compared to the stuff at the far end of the room, seems to be flipping about like this. Now, here's the next step. What you do now is hold your finger out at the end of your arm, do the same thing again. And then what you see when you do that is your finger still seems to kind of flip about, but it doesn't flip about as far. And in fact, if you could hold your finger on the end of a very long stick, then it would hardly move at all, okay? So basically this way, with a bit of maths, I won't do the maths, I promise, but you can work out how far away your finger is this way, because the further away it is, the smaller the wiggle when you shut one eye and the other. Okay, so what's this got to do with stars? Now, imagine this is the sun, and we're here on planet Earth, and let's say it's winter here, but we're going round the sun, so 6 months' time it's summer and we're over here, okay? So we can be in very different places with respect to the sun. Now imagine I'm looking at some very distant stars over in this direction, but there's a near star somewhere on the way to those stars. So when I look at the distant stars and the near star on opposite sides of the Earth's orbit, you get exactly the same thing. The near star wiggles about with respect to the far stars. And that's how you can tell how far away the stars are. You said, well, does it really happen? Well, it does, and I'll show you that. So let's go back to the pictures again. Okay, so this is a cartoon, but it's because it's slightly exaggerated, but this is what you see. In this picture, this is two views of the same bit of sky at different times of year, summer and winter. So the white stars are very far away, and they don't change their positions in summer and winter. But the orange star there is one that's meant to be quite close to us, and you see it wiggle with respect to the distant stars. And the further away the orange star is, the less the wiggle is. So in exactly the same way that you do with your finger and looking at a distant thing and shutting one eye. So the distance between your eyes is like the distance between summer and winter in the Earth's orbit. And that's how we can work out how far away stars are. So there's a little GIF here giving you the idea. Now, this is quite exaggerated, but it does it. So this illustrates the Earth going around the sun, looking at a nearby star, that's the red one, and the distant stars, it's given by this yellow line. And the effect you see in the picture up the top there is the distant stars staying where they are and the nearby star doing a waggle. So the simulation runs this twice, okay? So it does it for a nearby star like there's a big waggle, and then a further away star, we'll see it flip to in a minute. There we go, and here's the further away star, and that does a much smaller waggle. So it's exactly the same. Okay, but the size of that, as I said, that's still a simulation, and in fact is highly exaggerated, because the size of that waggle is very small. To give you an idea, if you were to imagine a person standing at the far side of Edinburgh, roughly speaking, and you're looking at one side of their head versus the other side of their head, then the angular distance, the difference between in the pointing direction of either side of someone's head, that's about the size of wiggle that nearby stars are actually doing. So it's really quite small, but you can do it with a good telescope. You can measure that kind of size of wiggle, but only a few stars are near enough to give us even that size of wiggle. So until a few years ago, we could only measure the distance to a few hundred stars out of the millions and billions that there are. We want to do much better than that. So the way we've been able to do that is get into space with an instrument. I'll show you a picture of this satellite in a minute. It's called Gaia, and it's with no disturbance from the atmosphere and all sorts of clever technological things. Rather than measuring the waggle from one side of someone's head to the other, it can measure this distance from one side of a human hair to the other. So it's an incredible technical achievement. I'll just show you a picture of the satellite just for fun to close up. So that's it, top left there. That's an artist's impression of what's out there in space, measuring the skies for us now. And it's been fantastic. It's a European Space Agency thing. It has a small contribution from the Americans, but it's mostly European. And it's a fantastic success. And it's been measuring the distances to many millions of stars. And now, instead of just measuring stars that are very near to us, we can measure stars clean across the Milky Way and really kind of measure out the structure of our own galaxy that we live in. So it's a fantastic advance in modern astronomy, and it's going to make a difference to science for many years to come. So that's the Gaia satellite, very proud European achievement. Okay, so that's how we know how far away the stars are. I'm going to stop there. Thank you.
Thanks a lot, Andy. Yep, just as before, if anyone has any questions, just pop into that Q&A button and I will be able to read it out to Andy.
I think everybody's being very shy this morning.
Well, maybe let me begin, Andy, by asking a question here. So when you try to measure the wiggle of the star in the sky, do you rely on a fixed background to be able to tell that something is actually moving in the sky?
You do indeed. So in principle, you could see some kind of middle-sized stars with tiny wiggles, but there are some stars that are so far away that effectively, so Gaia has to solve exactly that problem very carefully, knowing that actually there are big wiggles and middly wiggles and tiny wiggles, and it just sorts the whole thing out mathematically. But in traditional astronomy from the ground, you basically assume that the stars that move that are very nearby are very rare, and just about all the other stars don't move at all. And you kind of roughly break it down into those two camps.
I see. Thanks, Andy. There is a question from the audience. So the question is, how far away is the nearest star?
The nearest star, and the one that Thomas Henderson measured, is Alpha Centauri, and it's well, in astronomers speak, it's 1.3 parsecs, but that doesn't really help much. It's about 4 light years. So I can't remember what this is in kilometers, right? But basically, it's the distance that light will travel over 4 years. So that's the distance to the nearest star. It's many times further larger than the size of the solar system than any of the planets. And all the other stars are basically thousands of times further still. So yeah, about 4 light years. I hope that's a satisfactory answer.
That is quite a long way away.
It is.
Yeah. Right, let me just quickly check. Oh, somebody I think has worked out that 4 light years. Too many zeros. Sorry, I'm not going to read this out. It's 13 zeros. Yeah, thank you. Yes, it is indeed quite a long way away. It seems that we don't have any more questions. I guess, thanks a lot, Andy.
The question.
My pleasure.
Would it be okay if I asked a question before I?
Oh, yeah, sorry. Yeah, we have one from the panelists. Yes, go ahead, please.
So, can you measure distances for stars that are too far away to wiggle?
Did I plant this question? No. So getting back to what I said at the beginning, that when you look at the plough and you say, well, probably those bright stars are much closer. That does turn out to be true. So what you can do is, once you've got the distances to some stars, then you can divide them into types of their colors, for instance, and you can see that their absolute powerfulness depends on their colors. And then if you spot another star that's that sort of color, you can say, oh, I think that's like this other one. It's about this powerful. And then you can work out how far away it is that way. So there are other methods. None of them are as good or as safe or reliable as using the parallax method, but there are some other ways. I can see Beth's eager to get on.
Yeah, on that note, sorry, Abby is having tech issues, so I'm going to jump in and introduce our next talk. So our next talk is Beth Miller, who
so Abby very rudely has asked me to leave, because maybe we can only have so many at once.
It's because you're pinned, and so Beth would be talking with your face, which would be very strange.
Should I go ahead and share my slides? I'm not here.
Yeah, sorry, yeah, start whenever you'd like, Beth.
All right. Let's find the slides first. 1 second. So I am going to talk about planets, but not the planets in our own solar system. I'm going to talk about planets orbiting other stars. So as you know already, we have 8 planets in our own solar system. And we now know of thousands of planets orbiting other stars. So this is a graph, and along this axis, this is our x-axis, is the length of each of the year of these planets that we have plotted here. So the Earth would be right about here, 365 days in a year. And then over here, we have plotted the size of the planet. So how its radius compares to the Earth. So this is one Earth radius. So here's Earth. Earth would be about right here on this plot. And then larger planets are up higher. Here's where Jupiter would be. Here's where Neptune would be. So we can see that we've discovered many, many, many planets. Most of them are very different than the Earth. So there are a whole variety of different kinds of planets, some of which we see in our own solar system, and some of them we don't. So for instance, gas giants. We have 2 of those in our own solar system. So we have Jupiter and Saturn, and in our own solar system, they sit pretty far away from the sun, about 5 to 10 times further away than the Earth sits. We've detected a lot of gas giants around other stars as well, but they're not always in the same place as they are in our own solar system. So a lot of them are what we refer to as hot Jupiters. So that'd be like if you took Jupiter, but put it really, really close to the sun. So it was really hot, like the temperature of Mercury. And there's hundreds of planets like that. Then there's also Neptune-like planets. Again, we have 2 of these in our solar system. We have Neptune and Uranus, and they're really far out, right? So they are like 15 to 30 times as far away from the sun as the Earth like. So they're gassy and they don't have surfaces like Saturn and Jupiter, but they're a bit smaller. And we see these in other solar systems, far away, but also really close in. Like the hot Jupiters, we also see hot Neptunes and hot Uranuses. And then we also, in our own solar system, have terrestrial planets. So the Earth is a terrestrial planet, and these are planets that are mostly rocky with just a little bit of an atmosphere around them. Some have oceans, some may be habitable. Obviously, the one we're on right now is habitable, but some are not. Some may be more like Mercury or like Venus with a thick atmosphere that is definitely not habitable. And what's really interesting is among those thousands of exoplanets, there are also types of planets that we don't have in our own solar system at all, like the ones in this bottom right corner, so super Earths. So they tend to be rocky, like our own planet, but much bigger. So they're in between in size between our own planet and the size of Neptune. Some of them may have atmospheres, some may not. They may have very thick atmospheres. And in fact, they're really common around other stars, but we don't have any of them in our own solar system. Now, the planets that we're probably, well, as humans, we're kind of most interested in is the ones that might be habitable, the ones like Earth that could host life. So what do we mean by that? Well, it's really hard to tell if a planet is habitable or not. And I'll talk about that in terms of how we actually detect them. But usually, if a planet could be habitable, it lies in what we call the habitable zone. So this is our second graph of the talk. So on this axis, this direction here, we're plotting how far a planet is from its star. And this is the size of the different stars. So if our sun is kind of a medium-sized star and it's medium bright and medium hot. So that's why this is the area around the star in distance where you can have a planet that could have liquid water on its surface, like the Earth. Now, if you take a bigger star, it's hotter and it's essentially putting out more energy because it's bigger. And that means that that habitable position around the star moves further out. And if you take a lower mass star, it is smaller and cooler, it produces less energy, and that area needs to move closer in. So we're looking for planets specifically at these particular distances from their stars. These are the ones that could have liquid water and then could be habitable. And we've actually found a few of those, but not around stars like our own sun, mostly around these small red stars. So Andy had a question in the last talk about the very nearest star to the sun. It's actually a triple system. So there's Alpha Centauri, A and B, and then it has a wide companion star. All three are orbiting each other, and that star is named Proxima Centauri. So Proxima Centauri is one of these small red stars, and Alpha Centauri A and B are stars kind of the same size as our sun. And this is an artist's impression of what the surface of this planet that's been detected orbiting Proxima Centauri might look like. So you would see Proxima Centauri, but you'd also see the other two stars in the system in the sky. So this is a planet that is roughly at the right distance from its star to potentially have liquid water on its surface. But whether it does or not, we don't really know yet. But how did we find this planet? How do we know it's there in the first place? This was a planet that was found because it is making its star wobble. So it's making this star appear to wobble when we measure it from the Earth. So how to understand this? Here is a couple diagrams that show this. So we think of gravity as keeping the planet in orbit around its star. So the gravity of the star keeps the planet in its orbit, but the gravity of the planet is also tugging on the star. So the star is wobbling just slightly compared to if it didn't have a planet. So on the left, that's if we looked at it from the top down. We see it kind of wobbling in a circle. And then on the right, if you're looking at the planet in a different angle from the edge, you just kind of see the star wobble on the sky. And that's what we measure. We're looking at that very small wobble of the star to detect those planets, that particular habitable zone planet. So now I'm going to show you a few more habitable zone planets around a different star. Also an artist's impression here. And this is the TRAPPIST-1 system. So the star, again, is a very small, very red, very cool star. Well, cool for a star. It's not actually that cool. It's maybe the same temperature as a candle flame. And then we have these 7 different planets orbiting this particular star. And these middle 3 planets are about the right distance from their star to potentially have liquid water on their surface. So how were these detected? These were detected in a different way from the Proxima Centauri planet. These were detected because the geometry of the system is just right, that the planet passes in front of its star along a line of sight. And that means as it passes in front of the star, if we're just looking at the star from the Earth, the star will appear to get dimmer. So on the bottom, this is time that we're plotting, and this is how bright the star appears. And it just appears to dim just a little bit as the planet passes in front of the star. So all 7 of these planets were detected because we were looking at their star, and over time we just saw 7 different little dips of light that would repeat once a year, the year for each of those planets. So those are a bunch of habitable zone planets we know, but how do we know if they're actually habitable? In fact, we don't. And we can speculate about what they might be like, but we don't really know. So here's an interesting speculation. This is one of these NASA Exoplanet Travel Bureau posters you may have seen. They're really fun. This is for Kepler 186f, another habitable zone planet around another small red star. And if you notice, the caption here is where the grass is always redder on the other side. So here we have a planet that maybe the vegetation uses a way of transferring energy from light. So plants on Earth use chlorophyll, which is a green pigment, and that makes sense given the color of light that we get from our star. But if you had a much redder, cooler, dimmer star and the light was coming out in red instead of yellow and green, then maybe you would want to use a red pigment as well. But we don't actually know because we've only detected these planets indirectly. So to really understand their atmospheres, we need to directly detect them. And one way of doing that is direct imaging. So this is when we actually just take a picture of a planet around a star. But that's really challenging. So that's like trying to take a picture of a firefly next to a lighthouse. But if we have our firefly in our lighthouse, we're not looking at it from the beach. If we're here in Edinburgh using this model, our firefly in our lighthouse would be in Dublin. So taking a picture of a planet is like taking a picture of a firefly next to a lighthouse in Dublin from Edinburgh. So it's challenging to do so, but we've done it. And I'll end with a picture of a planet, several planets. And this is what this looks like. This is a series of pictures of planets over a decade. So you can actually see the planets orbiting their stars. Each of these little points of light is the light from a planet around the star. And these planets are really pretty massive. They are about 2 to 10 times as heavy as Jupiter, but much younger. So we're actually seeing them because since they're younger, they're hotter and they're still glowing with their own light. I think I'm going to end there, and I'm happy to take questions. I can tell you a little bit more about these planets too, which I like to call baby Jupiters.
Thanks a lot, Beth. I think we've really got a question from the audience. So the first one is, why do we think that life needs water and the same conditions as on Earth? Could life survive with different conditions?
That's a really good question. You could imagine maybe somewhere you could have silicon-based life or life not as we know it, but we don't have any examples for that. So the easiest thing to do, given that we have the example of what life looks like on Earth, is to start our search by looking for water.
Okay, thanks a lot, Beth. I hope that answers the question. So if you are new to the this chat, if you want to ask any questions, just pop the question into the Q&A button at the bottom in the toolbar, and we'll answer them very quickly. Okay, while we wait, maybe I can ask a quick question. So in recent years, we heard a lot of news about Mars, where there's water on Mars, but besides our own solar system, do you know any other potential candidates that are reasonably close to us that could support life?
So there are a few habitable zone planets in nearby systems, like the Proxima Centauri b planet and the TRAPPIST-1 planets. They could potentially, we also have other somewhat hotter exoplanets that we have detections of water vapor in their atmospheres. We don't have any clear detections of liquid water yet, but that is probably coming. Now, the tricky thing is most of those planets that we know around other stars are around these small red stars. And so they're very different than the sun. And one of the differences is that they're actually much more active. They produce a lot more X-rays and gamma rays comparatively than our own star. So they may not be great places for life because of that. Because if you have too much X-rays and gamma rays, you might not keep an atmosphere around your planet. The star itself may actually make the planet not habitable. We don't know yet whether those planets are habitable.
I see, thank you. It's quite a complex question, really. Does take a lot of research effort. I think it looks like we don't have any more questions from the audience.
Could I ask a question? Sorry.
Oh, sorry, Abby. Yeah.
I was going to, Jo, are you trying to ask a question?
Yes, I was going to, but you can go ahead.
I was just going to say, if anyone's got any more questions, they're welcome to add them in the Q&A, and Beth can respond in there as well. So if you think of something during one of the next sessions, that's a good place to interact as well, because I was going to introduce you, Jo, but if you want to ask a question before you start your session, you're more than welcome to.
I'll ask one question first, which is, if we could, like in an imaginary universe where interstellar travel would be possible, if you could go and visit one of these weird exoplanets, like where would you go?
That's a really good question. I have to choose just one, though? That's really hard.
Your top destination.
Top destination. I would love those 4 planets I showed you the picture of with them orbiting. I would love to see them in person. That would be great. And it's not that that's entirely like, so the Proxima Centauri, the nearest star to us, we could send a probe there, or even people. It would just take thousands of years. I guess that's pretty challenging.
Thank you.
Thank you very much, Beth, for that talk. It was lovely. And thanks, Mike, for sharing the questions. I'm now going to pass on to our next speaker, who you've just seen asking a question as well. So welcome to the Zoom webinar, Jo.
Can everybody hear me okay? Can I check that my sound's all right? Brilliant. Okay, I'll try and share my screen now. There we go. Can everybody see my slides as well? Yes? Perfect. Okay, so hello everyone. My name's Jo. I'm a researcher at the UK Astronomy Technology Centre at the Royal Observatory. And I'm going to talk a bit about invisible light and how we can use invisible light to explore the hidden universe across the electromagnetic spectrum. So I'll start off by just saying a little bit about astronomy as a science and what I think makes it quite unique, which is the fact that we can't go out and do experiments on a lot of the objects we want to study. So as the last few talks have highlighted, stars and planets, exoplanets are very, very far away, way beyond where we can travel. Galaxies are even further away. So we can't just go scoop out a piece of a star and see what it's made of. The main tool that we use in astronomy is the light that we get from those objects. So almost everything we know about the universe, the very distant universe, is based on the kinds of light that we get from the universe. So let's first of all talk about the light that we can see with our eyes, visible light, and then we can move on to what I mean by invisible light. So visible light, the light that we can see with our eyes, for example, is made up of lots of different colors of light. So if we take white light that we get from the sun, for example, we can split up that white light using a prism that you can see in the lower left of this image. We can split up that light into all of the colors that make up that white light. And we see this happening in nature when we see a rainbow. So for example, when you see a rainbow in the sky, it's the tiny water droplets in the air that are acting like these prisms and splitting up the light into all of its constituent colors. So this rainbow of light, all of the different colors that make up white light, can also be called a spectrum of light. So this is the spectrum of the white light that we get from the sun. And these are the colors of light that we can see with our eyes. And if we look at this spectrum and what it means in terms of physics, the color of the light actually holds a lot of really interesting information. The color of light corresponds to the amount of energy that it carries. The light acts as a wave, so we can also talk about this as the wavelength of the light. So long wavelength light, so the red end of this rainbow spectrum, is lower energy light than if we go up to shorter wavelengths of light across the colors of the spectrum up to the blue and the violet, then we get to high energy colors of light. So just by looking at the color of the light of different things in space, we can tell the energy scales of the physical processes going on. So here's an example of that. Here's a picture of a beautiful spiral galaxy. This is a galaxy containing hundreds of billions of stars. It's in the distant universe, and we've taken a picture of it here in the visible light that we can see with our eyes. Now, almost all of the light in this image is coming from the stars in that galaxy, but we can see that they're not all the same color. In the outskirts of the galaxy, so in these spiral arms that sweep out from the center, we can see bright blue light coming from very, very hot blue stars. Now, blue stars are, we already said that blue light is higher energy light. So these blue stars are higher energy than these cooler red stars. So we've got very, very hot blue stars in the outskirts of this galaxy. And if we move into the middle of the galaxy, you can see that there's a change in the color. We've got orange and red and yellow light coming from these stars in the center, which we know are lower energy lights with longer wavelengths. So we know that these stars are cooler. They're not as hot as those very, very bright, hot blue stars that we see in the outskirts. They've got lower energies, lower temperatures, and we've got cooler stars there. So just by looking at the color of the light in this image, we can learn a little bit about the physics of what's going on in this galaxy. And then that prompts a whole load of other questions. Why do we have these cooler stars in the center of this galaxy and these hotter stars in the outskirts of the galaxy? And suddenly we can start to explore some of the physics about how galaxies form and how galaxies evolve and why they have these structures and colors. Another really beautiful example of using visible light to learn about what's going on in objects in space is in planetary nebulae. So this is a nebula, the Helix Nebula, and something like this happens when a star reaches the end of its lifetime and puffs off all the gas from the outskirts of the star out into space. So what we can see here is the end result of that sometime later. And we can see that that gas is not all the same color. So we've got different colors, the bluish color in the middle going to the reddish color on the outside. Again, these colors of light correspond to energies. And in this case, they correspond to very specific energies. And those energies of light we know are associated with different chemicals. So just the light from this image tells us a lot about the chemistry of the gas that is surrounding this former star. And we can learn about the chemistry of these processes as well. So that's great. We've talked about visible light, the light we can see with our eyes. Also, we could call it optical light, but that's only a tiny part of the full spectrum of light. So as I said, light is a wave. It's an electromagnetic wave. And the electromagnetic spectrum stretches a lot further than that rainbow spectrum that we've looked at so far. So it's just a tiny part of it. If we go to lower energies, to longer wavelengths of light, we get into the infrared. We can keep going to lower and lower energies, longer and longer wavelengths down to the radio. If we go from the visible up to higher energies, we get to ultraviolet light, even further to X-ray and to gamma rays, the highest energy radiation. All of these kinds of radiation are a kind of light. Essentially, they're all electromagnetic waves, but there's only a small part of that spectrum that's visible. So I would call everything else here, so radio, infrared, ultraviolet, gamma rays, all of that I would call invisible light. And we saw how much information we could pull out of an image when it's just in that visible light that we can see. There is so much more information hidden in the other colors of invisible light that we can use, we can pull out to learn about the physics of what's going on in the universe. So just like with the visible light, these low energy, long wavelengths at this end and the short wavelength, high energy at that end. So if we want to learn about the most high energy explosive processes in the universe, we can look up in those high energy types of light to see if we can see what's going on. To do so, we need some very special kinds of telescopes. So obviously we can't see that radiation with our eyes, and we can't see it with a normal telescope, an optical telescope. So we need to create telescopes that can observe all of these different kinds of invisible light as well. Sometimes that can be very challenging. So for example, to look at the ultraviolet or X-ray colors of invisible light, we need to put telescopes in space. And that's because our atmosphere blocks that radiation. And that's really good for us because both of those kinds of radiation are not good for our bodies. So our atmosphere keeps us safe in that respect. But for astronomers who want to look at the ultraviolet sky, it makes it very difficult. So we need to put telescopes above the atmosphere so we can see what ultraviolet emission is coming from space. So you might recognize some of the names of these telescopes, the Hubble Space Telescope, for example, which is just a little bit older than me now. And it's taken images in the visible light. So some of the images that you might have seen of these beautiful things in space, nebulae and galaxies, some of the most stunning images have been taken with Hubble, but that's just the visible light. When we combine the images from Hubble with other kinds of information, we can learn more about the physics. We can make pretty pictures, but we can also learn about what's going on. So for example, Herschel was an infrared telescope that told us a lot about the dust in the universe. Dust doesn't sound particularly exciting, but I really love studying dust. It holds lots of information about stars being born. We've got these incredibly huge radio telescopes like the Very Large Array, ALMA, which is a kind of millimeter telescope. Up here, Chandra on the top right is an X-ray telescope that has shown us some of the most high energy processes in the universe. So I'll show you a bit about how we can combine that information to learn more about what's going on in these very distant objects. Let's look at this example of the Andromeda galaxy. So the Andromeda galaxy is our nearest neighbor, large galaxy. It's 2.5 million light years away, but it's a big spiral galaxy, a bit like our own galaxy, the Milky Way. And this is an image of it in the visible light. And we can see the light from the stars and these dark patches here, which are the light being blocked by dust. So this is what we can see if we were to look at it through a telescope that captures the light that our eyes can see. If we look at it across the electromagnetic spectrum, across all of these different colors of invisible light, we can see lots more information about what's going on. So first of all, if we look in the infrared, we can see that the brightest parts in that infrared image correspond to the darkest parts in the optical image. And that's because in the infrared, we're looking at cooler things, we're looking at dust. And while the dust blocks light in the optical, it actually glows really brightly in the infrared. So we can start to investigate the dust in more detail as we look in the infrared. If we go to the ultraviolet, we can see those higher energy processes, and you can see only the very brightest, bluest stars in the outskirts of the galaxy. So we can see those very, very hot stars. I think we might be running out of time. So I am going to stop there, but I hope this gave you a bit of an idea about how we can use light and different kinds of light to learn more about the universe. So thank you very much.
Thanks a lot, Joe. That was very interesting. There are all sorts of telescopes. So we do have time for 2 short questions, or long questions from the audience. And if you do, you just pop into the Q&A button. And currently I don't see any. So maybe I could ask a quick question. So I saw this image where you showed a lot of telescopes, some in space, some on the ground. And I did notice that for the radio spectrum, the telescopes looked like they had really big dishes. So can you maybe just talk a little bit about the design of these telescopes with respect to the spectrum, part of the spectrum they're trying to detect?
Sure. So you need to develop, like I said, specific kinds of telescopes to look at different parts of the spectrum. In the visible light and the optical light that you can see with our eyes, we can have a large single dish or big mirror essentially that captures the light. That might be, anything from a few centimeters to a few meters across in size. The bigger the mirror, the more detail we can see. So it's not about how far away we can see, but the more detail and the fainter objects we can see with one of these with a big mirror. Now, when we get to those really long wavelengths, the wavelength of light actually corresponds to how big we need to make the mirror to get that detail. When we go to a longer wavelength, we need a very, very big mirror or dish to collect all of that light at these long wavelengths. So to build a single dish telescope that gives us that kind of information, we need to build a dish hundreds of meters across. And these do exist. There are these huge, they look like, you know, giant satellite dishes in the ground. But there's actually a clever way to connect up telescopes called interferometry, where we can use lots of dishes together. We can connect them together to act as one very, very big dish. Yes.
Okay.
Sorry, I realized I dropped my microphone, so I hope you could actually hear that answer. I apologize.
Yeah, it was clear. It was just a little bit quieter, but I did hear you. Yeah.
That's okay. And maybe you could type some of that into the Q&A box as well, Joe, so that it's there in case anybody missed some of that. And I think we do have our fifth and final speaker here. I understand that there has been some tech challenges, but I hope we're all like ready to go. We've got a smile and a thumbs up, so that's a good sign. So I'm delighted to hand over to our final speaker of this session, Agatha.
Yeah, hi, my name is Agatha Rožek. I'm a postdoctoral research associate here at the University of Edinburgh. Many of you probably have already seen my workplace, which I have been at for a year and a half now, but because of the current situation, I have not visited the observatory actually. So I'm speaking to you virtually from the open doors here at my house. I do apologize if one of my kids manages to sneak in while I talk. So I'm going to speak about asteroids, which are commonly referred to as rocks in space. What I study is our closest space neighborhood, our solar system. And our solar system, at the center of our solar system, is this star called the Sun. And around the Sun, we have planets traveling around it on almost circular paths. So we have Mercury, which is closest to the Sun. Then there's Venus, Earth, Mars, Jupiter, Saturn, Uranus, Neptune, and then there's other stuff beyond that is much smaller than any of the planets. And between orbits of Mars and Jupiter, there is what we call asteroid belt, which is full of those little rocky worlds called asteroids. And some of them sometimes can come closer to Earth, and those are the ones that are most interesting to me. So they are funny little worlds. They are really small. So when we point our telescopes at them from Earth, we usually don't really see them. So we see them as little pinpricks of light. If you took a photo that has an asteroid in it and you're on Earth, you most likely wouldn't be able to recognize the asteroid from any other star that is in that photo. And this is the most of observations that I do. They look like that. So I take a series of pictures of sky, which has stars and asteroids in it. And at first, you can't really tell which is star, which is asteroid. But because we can calculate the positions of the asteroids, we know which one of those dots is the asteroid, and we can follow it as it moves along the star across the stars. And then what I do is I measure the brightness of all the stars and the brightness of the asteroid. And most of the stars that I try to look at usually just stay the same brightness throughout the observations. And then my little asteroid can go brighter or dimmer, and it changes its brightness. And this is because asteroids are not all like spheres. They have all sorts of different weird shapes. And as they rotate, because everything in space just rotates, they can reflect sunlight. And sometimes they reflect more of it, sometimes they reflect less of it. But when they reflect more of it, like they are brighter. When they reflect less light, they would be dimmer. And then what we can do, what I do as part of my job, is measure those changes in brightness. And from that, I can reconstruct how those asteroids look like. And I have a few examples here to show you. So one of such asteroids, sometimes they look like this. So they look like little space diamonds. I hope that's visible. So you can see this one is black. Most asteroids are almost black. They are very, very dark. But you can still see how the light from the window over there gets reflected from the surface. And sometimes it reflects more of the light, sometimes it reflects almost none at all. So you can see here it would be the brighter part. That's where I would see my little star like object getting brighter. And right here, I would see hardly any light coming from it at all. Of course, all the light coming from the asteroids that I detect comes actually from the sun, and it's the sunlight that is reflected off the asteroid surface. So this object specifically is an asteroid that I was looking at when I was working towards my doctorate. So this is the shape that I calculated for this asteroid to have. And it looks like a little diamond. And a lot of asteroids that we look at have this similar kind of diamond-like shape, but that's not the only option. Another option is for them to be very elongated. And if they're very elongated, you can see very strong differences between the brightness at their brightest and their brightness when they are the faintest. So this one would change its brightness in a very delicate way, like this. Now, when you look at something like this, which is very elongated, so you can see that it has one side is very long, it rotates something like this. So there is a huge difference between when we look at it sideways and when we look at it when the long side. So when we look at it when the long side is reflecting light, and when we look at it when the short side is reflecting light. And you can see that in those changes of brightness that you record from the photos, because they would be very strong and very deep. So this is the two types of asteroids. And you can tell that they're different types just by taking pictures of them in a series and measuring their brightness from those pictures. Another thing that we can do to look at asteroids from Earth is to use radar. Radars are a device that we often associate with like space flight, not space flight, with airplanes. You can see radar systems on airports which help to detect where aircraft are around the airport, for example. But radars can be also used as a method of detecting something that is far away. And they can be used to detect even asteroids in space. Of course, such asteroid has to be close enough to us to be able to detect with radar, and the radar has to be powerful enough, but with a strong enough. And the way it works, so we actually send the light that gets reflected by the asteroid. So with those observations that I was talking about before, similar to what's happening here, when you're looking at it, when I'm showing it to you right now, you can see my little artificial asteroid reflecting sunlight towards you. But this is sunlight coming from my window. With radar experiment, it's like shining a massive torch on asteroid and detecting the light of that torch. Only that torch doesn't shine light that you could see, it shines radio waves. So you shine radio waves on asteroids and they reflect those radio waves, and you can you can detect that signal, and that creates images of asteroids, and that can be also used to reconstruct shapes. And this is like the most powerful tool we have to learn about shapes of asteroids from Earth, because it can give us information about many, many details of the surfaces of asteroids. So when we look at them with this technique, they are all very smooth. When we take radar observations, we see more complex shapes. So this is one of asteroid. This is asteroid Galevka, which was detected with radar, and it looks a bit like a fist. It has this weird crevice right here. I find it really fancy. And there's another one. There's a few that look like this that we've seen in radar images so far that wouldn't be possible to see just from the changes of brightness. So they look like they're just two things stuck together. And that's what we do with asteroids, and that's how we learn about shapes of asteroids from Earth. Yeah.
Thanks a lot, Sakata.
Okay.
So as before, so if you have any questions, just pop into the Q&A chat. So I have probably an unrelated question to what you just described. Suppose there's an asteroid that just fell from the sky. What should we do to it? I mean, what should we do to help you, people like you, to research? I mean, first of all, if we do find something that looks like an asteroid, how could we be sure, you know, if it's somewhere out in the open, and what should we do about it? I know it's a bit unrelated to what, but just curiosity. Yeah.
Yeah, that's more a question to meteor experts. It's not that easy to find an asteroid that fell from the sky, because when they are falling from the sky, they usually just burn in the atmosphere. So when we see meteors or fireballs in the sky, that's just asteroids burning up when they come hard into Earth's atmosphere. So most of it burns up on its way to the ground. And what ends up on the ground, it's dozens and dozens of little fragments. It's very rare and very difficult to find something bigger. So it's useful to talk to a local geologist, I guess, first of all, or astronomer, see if they can tell if that's a fragment of asteroid or not. But it's very, very, very hard to find one.
I see, you had to be very lucky then.
Yeah. There's expeditions. So there was a famous one a few years ago, I think it was 2014, where an asteroid was detected on its way to Earth. Then actually British astronomers looked at it while it was still in space and managed to do some characterization. Then Dutch airline pilots saw it enter atmosphere because they were just flying above the area where it was supposed to hit. So they saw it going, well, not just past them, but they did see, like, in the distance, the meteor coming in. And then it ended on the desert. And because it was on the desert, it was on the ground where it was quite easy to find. If something fell in Britain with all the vegetation and everything, it would be a hard find, yeah.
Right, I see. Thank you. So I think we don't have any more questions in the Q&A chat.
Everyone, a quick second in case there's anything that they've also wanted to ask someone from the Royal Observatory Edinburgh. So there's still time to pop something in the chat, and we'll be keeping an eye on that as well. Thank you very much all for joining us this morning. So our next event today is our Inclusive Astronomy Talk, which is at 12:30. I'm popping a link into the chat for that now. Make sure to pop over as well to the Virtual Open Days website. There's a link for that there for more activities and information. There's a map of the site on there. You can follow us on Twitter at Royal Obs, or visit our Visitor Centre website to find out more about other events like this in the future. So that's at www.roe.ac.uk/BC. Thanks again for joining. In a moment when I end this session, you should see a screen that allows you to go to the feedback survey. And we really appreciate any time you can take to give us any feedback on these sessions to help us improve them and make them even better. Have a lovely weekend, everyone. And thank you all to all of our panelists for all your time as well. You've been fantastic this morning.